Dear Boscales, welcome to this video presentation about the tender Immerwind. We as ILTYM expressed our interests in working out this tender with you a few weeks ago. In this presentation, we would like to inform you about the important results of our submitted tender. So to begin, a brief summary of the project description. So Boscalis wants to build an offshore wind farm in the German part of the North Sea, 25 nautic miles away from the Eemshaven in the Netherlands. This wind farm, named Immerwind, contains a total of 108 wind turbines with a combined capacity of 540 megawatts. While part of the construction work revolves around the transportation and installation of all 108 foundation elements. ILTYM is a specialized contractor in the field of offshore wind turbine foundations. We therefore immediately applied for the tender issued by Boscalis. In this presentation, we will talk to you about the chosen transport and installation vessels, the sea fastening, the installation equipment, the workability of the vessels, and of course the planning and costs of this project.
Boscalis has made the bus terminal available to us so that it can be used as a feeder port. The bus terminal is located in the Eemshaven in the province of Groningen. The bus terminal has a storage area of 21,000 square meters. That's enough to possibly store all monopiles and transition pieces required for the project. The requirements of the distributed load have also been taken into account. The monopiles and transition pieces can be picked up in Aalborg, Denmark at Blad Industries, located on the Langerak River. From the start of January, production will begin and approximately 3 foundations per week can be collected.
Our base harbor is in Denmark and our feeder port is in the Netherlands, so we have to ship our monopiles and transition pieces from Aalborg, Denmark to Eemshaven, Netherlands. There are 3 possible transport routes. The first and shortest route is through Denmark via a place called Tiburon. It is the shortest route but not the best option because there are many bridges and those bridges limit our dimensions of the transport ships we can use. The second route is a route through the Kiel channel. It is also not the best route because the channel has a speed limit, so it makes the travel time longer and results in more expenses. But it is a safer route because the waters are protected by land. So if the weather gets really bad, we can use this route as an alternative option. The third and last route is the best route, but it is the longest route, but it is also the most used route, and that's because it is open sea, so you can ship freely and speed up. There are no speed limits, so we use the longest route, but this results in the shortest transport time.
We compared several transport vessels. We put this into an MCA with a number of criteria. The halfway Trina came out on top. This is a vessel from the company Saal. It has 2 cranes that can lift 700 ton each. Together these cranes can lift a monopile, but one crane also has enough power to lift a monopile or transition piece. The ship sails at a speed of 20 knots. The reason this vessel was better than the other vessels is because of the area distribution efficiency. If the ship is bigger but can't carry more monopiles and transition pieces, it is less efficient in terms of cost. The ship can carry 4 monopiles and 4 transition pieces. 2 monopiles go in the hold and the other materials go on the deck, as the picture shows. The sea fastening are important to keep the monopiles and transition pieces in place. Another important purpose of the sea fastening is to distribute the heavy weight over the surface of the foundation. For the monopiles, multiply saddles are used to distribute the weight over a larger surface area. For a monopile, 4 saddles are used. The function of sea fastening and the transition pieces are the same. It is only more difficult to keep the transition piece in place because it's vertical on the ship. The transition piece is placed on ships on a grillage with a tube with jacks that clamps the transition piece from the inside. This is a sturdy way and it does not damage the outside. With convenient lifting tools, the monopiles and transition pieces can be easily and safely lifted onto and off the vessel. The monopile is lifted onto the vessel with the help of two cranes and slings in good balance. The transition pieces have a specially designed lifting tool that works with the clamping system. This is operated by a remote control so that no people have to climb into the transition piece.
The choice that ILTYM made for the installation vessels to be used is the Alpha Lift from the company Seaway and Boca Lift 1 from Boskalis. These are the two installation vessels that come out best from the multi-criteria analysis. These two vessels score particularly well on the fact that they have a high workability and, above all, can place many monopiles and transition pieces on deck. Particularly because of this, the project can be done faster and costs are saved. Also, we must not forget that without using these two installation vessels, the deadline of October 15th for installing the monopiles and transition pieces would not be met.
To install the foundation safely and in an easy way, several tools are needed on a ship to do everything. The gear especially needed for the monopiles and the transition pieces be described. To lift a monopile with one crane, a lifting spreading bar is used to balance the monopile. To lift the transition piece lifting tool from ILTYM is used to clamp the transition piece from the inside. To lift a monopile into the monopile gripper, a monopile upending tool from ILTYM is used. To hold a monopile in a place vertically in the water, a monopile gripper is used. The monopile then moves dead straight into the ground. To drive the monopile into the ground, a hydraulic impact hammer is used. To keep the monopiles and transition pieces in place on the installation vessel, the same sea fastening is used on the transport vessel. The grout to be placed between the monopile and the transition piece is made on site by a grout mixing jet. The grout is carried in large silos, and when the grout runs out, the transport ship replaces the silos.
Fallpipe vessels are needed for applying the scour protection layers. After comparing several fallpipe vessels with each other, we've opted for Jan de Nul Simon Steven. This vessel has a large rock carrying capacity, which means that we'll only need to sail back and forth a few times. This vessel is equipped with a ROV, so it can precisely survey its own work. Applying a filter or armor layer takes about 3 hours. Resupplying will take place at the Bremanger quarry in Svelgen, Norway. It takes about 55 hours of sailing to get there. After applying the filter layer, the array cable has to be installed, before we can begin applying the armor layer. We have estimated that each array cable installation will take about 1.5 days.
For every installation vessel, we have created our own installation cycle. In the table to the right, you can see the process of installment. If you pause the video here, you can take a closer look to see how the steps are going. For now, the important thing is that every foundation takes around 25 hours to produce. For the better result, we have taken a weather maintenance downtime into account. This is downtime when the ship is not producing anything. With this into account, it takes around 25 hours per foundation. For the transport vessels, we have made a different table. In this table, you can see with the different kind of speeds what every transportation vessel takes for travel time. Those times are taken into account in the logistics schedule.
The project area is in German waters, so we need to take the German regulations in account. The 4 regulations are listed on the screen. First, a soft start. Second, acoustic deterrent devices. Third, passive acoustic monotoning. Last, a noise restriction. A soft start means starting quietly for the first few minutes and quietly building up the piling. Acoustic deterrent devices is a device that deters the surrounding marine life before the piling exercise started, because the noise can be harmful for the marine life. Passive acoustic monitoring means that we have to monitor the sound distribution at all times. We want to do this by placing buoys in the water at a distance of 750 meters from the piling exercise and anchor them to the seabed. These buoys would be equipped with measuring equipment to measure the noise distribution. There is also a noise restriction at 160 decibels at 750 meters sound exposure level. Without a noise mitigation system, we would be above the 160 decibels, we would be around 170 decibels, so we want to use a noise mitigation screen. This screen can be lowered from the monopile grabber and we don't have to use another vessel. That's why we chose for this system. And the noise mitigation screen also decreases the noise distribution with 25 decibels, so we are under the 160 decibels noise restriction.
For the workability, we have looked at different kind of vessels. The workability is measured by the length of an installation vessel. If the vessel is longer, it has a better workability. In the table below, you can see the difference between every installation vessel we have looked at. For a jackup vessel, we've taken the 6 hours, and for something else, we have taken the 12 hours workability. With those numbers, you get the graphics to the right. Those graphic is meant for our vessel that we have chosen.
For the risk analysis, we have chosen for the ISO risk management standard. We have taken the following project risk into consideration: planning risk, budget risk, quality risk, environmental risk, health and safety risk, and resource risk.
For the logistics in the project, we first need to know how the installment will go. First, we have divided the foundations in 12 different strings. Those strings will be installed by the installation vessel, like you see in the table beneath. If you know how fast the foundations will be put into the ground, we can make a transport schedule for the transport vessels. The goal of the transport schedule is to keep the installation vessel fed with foundations. In the table to the right, you can see all the different steps the transportation vessel has taken to keep it fed. Like you can see in the graphics, the installation vessel will be fed the entire time the vessel is operating. With the schedule, the production of the Harbour won't run out of foundations and all goes well. Here is our planning. In the planning you can see the different phases we have taken to finish the project. The project will be having the multiple phases, like the filter layer phase, the transport phase, the installation phase, and the cable construction phase, and the armor layer phase. If you want to see a closer look, you can pause the video here to see how it will look at the end. The project will take around 345 days to finish. Here is the total cost of our project. The project will be around £108 million. That will mean £1 million for each foundation. In the table next to you, you see the different aspects we have taken into account for our project. If you want to see a closer at that, you can see the Excel in our files. Here you can see what different aspects we have taken into account. You can also take a break in the video to see how the table is constructed.
Thank you for watching our offshore wind farm tender video. We believe we have a strong proposal and are confident in our ability to deliver. We look forward to the next steps in this process.